It looks like the video didn't record for last time, so we're just going to go ahead and look at this presentation and make sure that we're comfortable with what's going on in the Chemical Kinetics Lab. So on here, I go through and discuss kinetics, but what we're talking about in a lot of this is the collision theory of chemistry and understanding that we have reactants that are colliding together and hopefully doing so in a successful way and either switching their components if we're doing like a double displacement reaction or decomposing and breaking apart, just depending on what the specific kind of reaction we're doing. But we can measure the change in one material, like how much of A do we have? Is there 2 moles to start with? Do we have only half a mole by the end? You know, how quickly did we get from that 2 moles to a half a mole? That change from 2 moles to a half a mole would be 2 minus a half, or 1.5. So that's how you would look at that math here in the reaction rates when we have concentration of H2 at point in time 2 minus concentration of H2 at point in time 1 over the change in time. That's where you get these definitions for the reaction. It's the change in material concentration over the change in time. If you lost 1.5 moles and it took 30 seconds, then you divide 1.5 moles by 30 seconds, and that gives you how long it took you to get rid of that material. And dividing them out gives you that average rate. So that's all we're doing, is having an initial measurement of something and then a means to understand when or how long it took all of that to react, so that we would have our change in material and our time it took for the reaction to occur in order to punch into this calculation of change in material over change in time. When we look at the differential rate law, it's just taking each of the materials into account. So if A and B are our reactants, we have a negative value here to show that they are depleting or going away with time. And then the C and D concentrations are going to be positive because we are increasing our amount of product as the reaction moves forward, hopefully going from 0 product to whatever our equilibrium concentration would be. When you're able to get these fractional components from their stoichiometric values. So the lowercase a would be from your stoichiometric value. So for H2 here, it is 2. For oxygen, the O2, we only have a 1 in front of it. And again, for water, we have a 2 in front of it. So A and B would be hydrogen and oxygen. We would have a 2 for lowercase a and a 1 for lowercase b, so that one wouldn't really count. And then if C was our water concentration, then we would have a 2 for our lowercase c. And then again, we would just measure our materials and try to understand how much of this material we have at any given time and track that change in concentration. While we're getting on the kinetics of a reaction, we need to talk about catalysts, because they have a chemical means to speed up the rate of a reaction and have us generate your product more quickly. Note that they don't really have any overall impact on the equilibrium or the amount of product that you can create overall. If a couple hours from now with no catalyst, you were going to have a 30% yield and only have 3 grams of something, then this would just give you that 30% yield, and you'd have your 3 grams just sooner. So it's not going to change a lot of the core components of the reaction, and it's not going to become part of the reactant or product in any way overall. It might temporarily bond to one or both of them, but then remove itself or be regenerated in some way. As we can see with this diagram, oftentimes they're thought of just as some sort of docking station for the reactants to come together, bond in the proper orientation, and then leave based on the overall surface structure. Sometimes this is a really simple model, but they generally are more selective and will only bond or interact with certain types of molecules or certain sizes of molecules, meaning that they'll allow you to tune the shapes and size of the catalyst openings to put the right reactants in it for the specific reaction. So again, catalysts do not become part of the product. They don't increase the mass of product produced. They are only there in the intermediate stage. So moving forward, talking about the rates of the reactions, we have a table here that has a lot of math on it that we are going to go through. But at the end of the day, it boils down to trying to figure out the order of the reactant, which, like I said before, kind of gives us this exponent that we put on our rate law, which the zero order reactant, we have a to the 0 power, which disappears. Anything to the 0 power is just going to be 1. So it's k times 1, or just k. And then the first order reactant has to the first power, just one A concentration here. And if we were to have double the change in a first order reactant, we would notice double the rate law change in rate. So triple a first order reactant would have triple the impact on a rate. But when we look at the second order, we have A squared, meaning that the A concentration is something that's very important to the reaction. And if we double the impact here, we would have 4 times the impact on the rate. Or if we tripled this, it would be like multiplying the rate by 9, because it has that much more of an impact on the rate of the reaction. So again, just think of the order of the reaction and how important it is to the rate, and how you can speed up the reaction with Le Chatelier's principle by adding more or less of something. This lets you know that adding all of the zero order reactant in the world isn't really going to change the rate of the reactant. You'll get more product, yeah, through Le Chatelier's principle. But you'd have to wait for the reaction to go to completion, and it might take a while for it to make all of your product. So we're able to rearrange the rate law and look at it in multiple different ways. The important part is trying to get the slope off of these values, because we can use the slope of our linear graph to calculate our rate value. And that's something that we're going to do later on with the data in the lab. So we have to plot our data either as, you see on the next slide, as concentration versus time, or 1 over concentration versus time, trying to figure out which means of graphing it gives you a linear graph and which means of graphing it gives you a curved graph. And when you get that linear graph, negative k generally will give you your value that you need to calculate your rate law. So with some of our data, you can tell that it's not exactly a perfect line, but there's usually one that definitely follows the curve better. And if you look at the R squared, like the linear regression for the data, you can see that some of them have a much higher correlation to that linear trend line than they would for the exponential or any other trend lines you might try to adjust them to. So you can use the R squared value to justify which one is linear, because it mathematically tells you which one is more linear based on how high that R squared value, or how close it is to 1. So once you determine which one of those graphs gives you your straight line, then you can compare that with the charts to tell you if you have a 0th, 1st, 2nd order for that reactant, and therefore you'd be able to know which rate law you would use, more or less changing this value here, or on the exponent, or using a different form of the integrated rate law, depending on which order the specific reactant was found to be. So I have just a fake example here of some data from before that is in a different spreadsheet. And if you double check what we're doing for each reactant, In the first blue rows we have here, we are using 1, 2, and 3 servings of reactant C. So we are doubling and tripling the concentration of C while leaving A and B the same. So we're just testing how strong C has an impact on the rate. And for this data, the rate doesn't change. So we would say that since it has 0 impact on the rate, it would be a 0 order reactant. And then the same thing happens for doubling and tripling the amount of A, and then doubling and tripling the amount of B. But then we have to double check what type of impact it would have on the rate. So for this data, when we double the value of A, we get double the value for our rate. And when we have triple the amount of A, we get triple the value for our rate, meaning that we had a 1-to-1 impact on our rate, and therefore A would be a first order reactant and have a 1 in the rate law. And then B, we notice it has a much more profound impact. So if you multiply 1 by 2 and double that, you multiply 2 by 4, meaning that it has a squared impact. 2 squared is 4. And instead of doubling, we have a quadruple or 2 to the second power impact on our rate. And that makes sense from the math. If it's a second order reactant, then whatever values you put in there, when you do the calculations, you would spit out a higher value for the rate. And the trend follows for doing triple the amount of B and getting not triple the amount, but 9 times the amount of your increase on your rate. So the overall reaction, we would say for this, is a third order reaction because it has 1 first order and 1 second order and 1 0. So when you add the 0, it doesn't make a difference. So this is how we would put it all together if we were to suss out exactly which were 0, which were first, and which were second order, and then have all of our reactants listed out for us here. So when we look at our data, like I said, some of them aren't exactly a perfect line, but you can tell which one is more linear and which one is kind of more of a curve. So you can be able to compare the graph that is our ln of concentration versus time here. This is our 1 over concentration here. But you can look back on the charts or look through the lab manual to see which things that would correspond to and be able to put that in your data and work that out in your lab summary. And like I said, if you look at the R² value for any trend line for the series, then that would be a way of mathematically justifying which one was more linear and which one was not, if you wanted to discuss that in your data. But if you have any questions, let me know. I'm sorry that the video wasn't posted sooner. I often have issues with WebEx. But if you have any questions, let me know. And if you want to do any in-person tutoring or do anything over WebEx, we can set something up. So just keep me updated.